The universe has always captivated humanity's imagination, drawing us to the stars and leading us to ask questions about its origin, structure, and ultimate fate. As we gaze out into the cosmos, we seek answers to some of the most fundamental questions of existence. Where did everything come from? How did the universe begin? What is it made of, and what lies beyond the stars? For over a century, one theory has dominated our understanding of the cosmos, the Big Bang theory. According to this theory, the universe began from an incredibly hot and dense state, rapidly expanding and cooling to form the stars, galaxies, and structures we see today. It was a groundbreaking idea that shifted our perception of the cosmos, providing an explanation for everything from the cosmic microwave background radiation to the distribution of galaxies. But as with any scientific theory, new discoveries can shake the very foundation of our understanding, and the latest discoveries from the James Webb Space Telescope are doing just that. The James Webb Space Telescope, launched in December 2021, is the most powerful space observatory ever built. Equipped with cutting-edge technology, it can capture infrared images of distant galaxies, nebulae, and other cosmic objects. Its observations are offering us unprecedented views of the universe, allowing us to peer back in time to moments just after the birth of the cosmos. And what it is revealing is astonishing. The discoveries made by the Webb telescope are not just awe-inspiring, they are forcing scientists to reconsider some of the most basic assumptions we have about the universe's origins, structure, and evolution. Before the advent of the James Webb Space Telescope, the standard model of cosmology was built around the Big Bang theory. The idea was simple yet profound. The universe began as a singularity, a point of infinite density and temperature, around 13.8 billion years ago. This singularity began to expand rapidly, cooling and eventually forming stars and galaxies. This theory helped explain much of what we observe in the cosmos, such as the cosmic microwave background radiation, the redshift of distant galaxies, and the distribution of galaxies across space. However, as scientists looked deeper into the universe, they began to encounter problems that didn't fit neatly into the Big Bang model. These problems were theoretical, yes, but also observational. The data we gathered from telescopes and space missions over the years pointed to phenomena that could not be easily explained by the existing theories. Yet the Big Bang theory held its ground until the James Webb Space Telescope came along. The discoveries coming from Webb have left scientists scratching their heads, challenging the very essence of the Big Bang theory. The telescope has revealed galaxies that appear to be much older than they should be, based on the established timeline of the universe's birth. Some of these galaxies, which appear to have formed only a few 100 million years after the Big Bang, are far too mature and massive to have developed so quickly. These ancient galaxies appear to contradict the predictions made by cosmologists, forcing scientists to confront the possibility that the universe may not have evolved in the way we thought. In essence, the James Webb Space Telescope is showing us a universe that doesn't quite fit the narrative we've constructed over the past century. And if the universe is revealing itself to be much more complex than we imagined, then our understanding of its origins, and its very nature, may need to be completely rethought. One of the scientists at the forefront of the Webb mission is John Mather, a Nobel laureate and the project's senior astrophysicist. Mather is a staunch advocate of the Big Bang theory and has spent much of his career working to confirm its validity. However, even Mather himself has been faced with the unsettling reality of the Webb telescope's discoveries. Despite his deep commitment to the Big Bang model, Mather has had to grapple with the idea that the universe may not be as straightforward as we once believed. In several interviews, he has expressed his belief that these newly discovered galaxies might have formed more rapidly than previously thought, perhaps due to faster processes of matter accumulation. But even Mather's explanations cannot fully reconcile the inconsistencies between the observations made by Webb and the traditional model of cosmology. The Webb telescope has also uncovered large galaxy clusters that appear to be much more evolved than expected, given their supposed age. These galaxy clusters, vast groups of galaxies bound together by gravity, should not exist in the early universe, or at least not in the form we see them now. The galaxies that make up these clusters are highly developed and appear to be much older than they should be based on the age of the universe. This is a profound puzzle for astronomers, as the models used to predict galaxy formation and evolution suggest that such complex structures should not have existed so early in the universe's history. What's more, these galaxy clusters are located in areas of space that we would have expected to be relatively empty, given the prevailing theory of the universe's expansion. The discovery of these massive structures challenges our understanding of how the universe evolved from its early stages, and it casts doubt on the accuracy of the Big Bang model as the definitive explanation for the cosmos. These observations are not just puzzling, they are paradigm-shifting. They force us to confront the possibility that the traditional Big Bang model may be incomplete or even incorrect. For decades, cosmologists have relied on the Big Bang theory to explain the structure of the universe, the formation of galaxies, and the distribution of matter across space. But if Webb's findings are correct, then much of our current understanding of the universe's birth and evolution could be called into question. And if the Big Bang theory is indeed flawed, then what other explanations might be available to account for these startling observations? There are several alternative theories that have been proposed over the years, each one offering a different perspective on the origins and structure of the universe. Some of these theories align with ideas from quantum mechanics and cosmology, while others draw on older models of the universe that were largely abandoned in favor of the Big Bang. One of the most intriguing alternatives is the multiverse theory, which posits that our universe is just one of many in a vast, infinite expanse of parallel universes. According to this theory, each universe has its own set of physical laws, and the conditions for the formation of galaxies and stars could vary dramatically from one universe to the next. If the multiverse theory is correct, then it could explain some of the strange discoveries made by the Webb telescope. Perhaps the early universe was not a singular event, but rather part of a much larger cosmic structure in which our universe is just one bubble among many. The idea of the multiverse is not just a speculative theory, it is grounded in certain interpretations of quantum mechanics and cosmology. In fact, some of the mathematical models that describe the behavior of quantum fields and particles suggest that multiple universes could coexist within a larger cosmic framework. These universes may have different laws of physics, different constants, and different properties, and the conditions for the formation of galaxies and stars could be vastly different from what we observe in our own universe. If this is the case, then the strange galaxies observed by the Webb telescope may not be as anomalous as they first appear. Instead, they could be the result of different physical conditions in a separate universe or even a different part of our own universe, where the laws of physics operate differently. Another alternative theory that has gained attention in recent years is the idea of a cyclical universe. This concept, championed by physicist Roger Penrose, suggests that the universe undergoes an infinite series of cycles, with each cycle consisting of a period of expansion followed by a collapse. In this model, the universe is eternal, and the Big Bang is just the latest phase in an ongoing cycle of creation and destruction. According to Penrose, the universe's expansion is followed by a contraction, during which all matter and energy collapse back into a singularity, only to be reborn in a new Big Bang. This theory would explain some of the oddities observed by the Webb telescope, such as the presence of ancient galaxies that appear to be much older than they should be. These galaxies could be remnants of previous cycles, objects that were created in a previous universe and carried over into the current one. The cyclical model of the universe offers an intriguing alternative to the Big Bang theory, and it may provide a way to explain the strange phenomena observed by the Webb telescope. Yet another possibility is that our universe is part of a larger, multidimensional structure, in which different pocket universes exist within a higher dimensional space. In this model, our universe would be just one of many that occupy a higher dimensional space, and the interactions between these universes could have a profound impact on the structure and evolution of each individual universe. This theory could help explain some of the strange phenomena observed by the Webb telescope, such as the rapid formation of galaxies and the existence of large galaxy clusters in regions where they shouldn't be. If the universe is part of a larger, multidimensional structure, then the conditions for galaxy formation and evolution could be very different from what we currently understand. These alternative theories offer exciting new possibilities, but they also come with their own set of challenges. For one, they often conflict with Einstein's theory of general relativity, which has been the cornerstone of our understanding of gravity and the structure of spacetime. The Big Bang theory, as it is currently understood, is based on Einstein's equations, which describe the expansion of the universe and the formation of galaxies. But the alternative models we're considering may require a complete revision of these equations, or even the development of entirely new theories to account for the strange new discoveries we're making. It's also important to remember that many of these alternative theories are still in their infancy, and there is much we don't yet know about how they might work in practice. Perhaps the most important takeaway from all of this is that we are living in a time of scientific uncertainty. The discoveries made by the James Webb Space Telescope have thrown a wrench into our understanding of the universe, forcing us to confront the limits of our knowledge and the possibility that our current models are incomplete or flawed. We are now at a crossroads in our understanding of the cosmos, where new theories and ideas must be explored, tested, and refined. It's an exciting time to be a part of the scientific community, as we are on the brink of potentially groundbreaking discoveries that could revolutionize our understanding of the universe. But it's also a time of humility, as we are reminded that the universe is far more complex than we ever imagined. In the coming years, as we continue to gather data from the Webb telescope and other observatories, we may find that the universe is far older, more intricate, and more mysterious than we've ever thought. And as we dive deeper into the unknown, we may discover that the answers we've been searching for are far more complex than we ever imagined.